In this video, I'm going to solve another example based on the actual transformer with losses. So here a 2300 by 230 volt 50 Hz distribution transformer has following parameters. So he gave us the primary voltage. This is V1, this is V2. Okay, so from there you can find N1 is to N2, which is 10 is to 1. Okay, now R1 value is given 0.286, X1 is 0.73 ohm, R2 3.19 milli ohm, and X2 J 7.3 milli ohm. R naught equal 1000 ohm, X naught equal to J 1250 ohm. This R naught represents the leak resistance of the core, and X naught represents the leakage reactance of the core. And the load impedance is given. So we don't know whether it is fully loaded, half loaded, since we don't know the rating of the transformer. Now he's asking us find the equivalent circuit of the transformer. XME are the short way to write it down. Transformer. All the impedance referring to the primary side, efficiency, voltage regulation, and when the transformer is connected to a 2300 volt supply. So the primary is connected to 2300 volt supply. He's asking about transfer everything, this secondary impedance into the primary side. Okay, now first thing we need to find the N value. Okay, N is the transformer ratio, or K value, which is N2 over N1. I have N2 equal to 1, N1 equal to 10, which is also equal to V2 over V1. If you want to, you can say V2 equal to 230, V1 equal to 2300. Okay, so I end up with N value as 0.1, so N square must be 0.01. Now I'm transferring secondary impedance to the primary side. So when I'm doing it, I need to multiply with I need to divide it by N square. So R2 prime, so this is R2. When I move the R2 onto the primary side, I call that as R2 prime. R2 prime equal to R2 over N square. R2 is 3.19 milli divided by N square is 0.01. That value is 0.319 ohm. So R2 prime is equivalent impedance of secondary looking at after transferring to the primary side. Now I always get confused whether do I multiply with N square or divided by N square. Now for example, I forgot and I multiplied by N square for example. So R2 prime equal to, say I multiplied with N square, then what happened? It is 3.19 milli times 0.01, which will gives me around 31.9 microohms. Okay, now compare your R1 and R2 prime. Your R1 is 0.286 ohm, R2 prime is 3.9 micro ohm. It's a way big difference. Okay, so for sure my calculation is wrong. That's how I usually check whether it is divided by N square or multiplied by N square. When we did the divided by N square, you see your R2 prime is 0.319, which is close enough. Need not to be very close, as long as it's within the limit, should be okay. So when you're transferring secondary impedance to the primary side, you just need to divide it by N square. At the same time, don't confuse with the A. N is the transformer ratio, A is the turns ratio. A is N1 by N2. Okay, so it's just opposite to N. So if you're using N, you need to do the opposite way. So to avoid confusion, I'm not going to use A anywhere. It's just N. N is transformer ratio. Now X2 prime equal to X2 over N square, which is 0.73 ohm. And the load impedance on the primary side, 0.387 over N square plus J 0.29 N square, which is 38.7 plus J 29 ohm. So this is the complete circuit after transferring everything onto the primary side. So here this I2 prime and I naught. Look at this number 1000 and J 1250, but these numbers are 38, 29, 0.319, 0.73. So if you look at here, I2 prime is very large compared to the I0 because of the impedance. Okay, here you have 1000 ohms, here you have only 40 ohms. So I2 prime is more. So I can say this I1 is approximately equal to I2 prime. So to simplify, to minimize our calculations, what I'm doing here, I'm moving this parallel combination from here to here. It's not going to make a big difference. Okay, so if I move it there, that's easy for me to add R1 x1 R2 prime x2 prime. This total is called total impedance looking on the primary side. Okay, Z01 is the total impedance looking from the primary side. Total impedance of the transformer, internal impedance, not including the load. So Z01 equal to 0.605 plus J 1.46 ohm. Z total equal to Z01 plus ZL. I'm talking about only this side. I'm not including the parallel combination because I want to find the I2 prime. Okay, so I2 prime is nothing but I1 approximately. Okay, so I2 prime equal to 2300 over Z total. So this is Z total, not including the parallel combination. So 2300 over Z total, which is 2300 over 39.305 plus J 30.46. When I convert this rectangular format into polar format, it's 49.72 at an angle of 37.77. So I2 prime, I found it. Now V2 prime is nothing but, which is the voltage drop across this load, is, I know the current, I know the impedance, so it's just I times R. I end up with 2237.13 at an angle of 0.923. As I discussed in the previous video, this must be very small. Okay, now percentage of voltage regulation. The percentage voltage regulation is nothing but V no load minus V full load over V full load. So if I disconnect this load, there won't be any current passing through it. The no load voltage must be 2300. So 2300, full load voltage must be 2237.13 over 2237.13 times 100. Usually voltage regulation is always in percentage, so it's a 2.81%. So as long as it's very close to 0, that's a good one, good transformer. If it is above, if it is close to 100, that's a very, very bad transformer. Okay, so now we're going to find the losses. So we have two kinds of losses. One is iron losses and copper losses. So this iron losses we can find out by using IW square times R naught. Here IW is nothing but the current passing through this resistor. This resistor indicates the core resistance. IW I can find out since it's a parallel circuit with the source. So 2300 divided by 1000, which is 2.3 amperes. So the core iron losses, also called core losses, okay, also called core losses, equal to 2.3 whole square times 1000, 5290. And copper losses always happen in the copper wire, so in the winding. So I2 prime times I2 prime square times R1 plus R2 prime. So I end up with 46.26 whole square. So the resistance of that whole winding is 0.605. So that is the resistance I used. So I end up with 1294.69 watt. Now output power is nothing but I2 prime square times RL. Remember, this P is always consumed inside the resistor. Okay, so I'm using only resistance of the load, which is 38.7. So I end up with 82.82 kilowatt. Now efficiency is nothing but P out over P out plus losses, which is P input. This is nothing but P input times 100. Efficiency is always output over input. 82.82 over 82.82 plus 5290, this is in watt. I'm going to convert that into kilowatt, which is 5.29 plus 1.295 times 100. So the efficiency of the transformer is 92.6%. Most of the times transformers are really high efficient machines compared to the motors and generators. Now he's also asking about V2 here. What is the voltage there? Now here, instead of 2300 volts, I'm getting only 2200. How much is that? 37. 2237. That's the voltage we found. 2237.13. So 2237.13 volt. Now can you guys tell me what is the voltage we're going to receive? V2 over V1 equal to N2 over N1. So my V2 equal to N2 1 over 10 times 2237.13. So my V2 must be 223.71 volt. I'm expecting 230 volt, but I'm receiving only 223.7 volt. Is it good for our equipment? Probably okay. I mean, most of the equipment you use, they're mostly designed, even though it says 120 volt, probably it can work between 110 to 130. Okay, but at the same time, it's not recommended to operate your equipment beyond that voltage. Even if it is further away from 120, it's not recommended to use that equipment with the lower voltage or higher voltage. Okay, I will stop this video here. So the next video, I'm going to work on SC test and OC test of a transformer. Thank you.